Hello and welcome. This is the first video I'm ever uploading to YouTube. I've wanted to make math videos for a while, but I just recently got this drawing pad so I can actually write things neatly. Unlike before where I was writing with my mouse. So today I'm going to talk about something that I found particularly interesting when I was in 8th grade. When my teacher told me that 0.9999 and so on is equivalent to 1. And at first I didn't really believe her because they don't look the same. One's a decimal and one's an integer. And in my mind I was kind of like, well, sure, this probably is very close to 1, but it can't be 1. But actually, being arbitrarily close to 1 is good enough to show equivalence. And there's a classic proof for this. I'll show it here. Probably seen this before. I'm going to show it this way, and I'm going to show it a different way. So this way says that if you let s equals 0.9 repeating, then clearly 10s is equal to 9.9 repeating. You're just going to move the decimal over 1 when you multiply by 10. So let's just subtract these quantities. We get 10s minus s. Well, we plug in these numbers, we're going to get 9.9 repeating minus 0.9 repeating. And clearly that's just going to be 9 because you're just getting rid of this after the decimal part. And 10s minus s is 9s. So this implies that s must be 1. But I already defined what s was. I already said that s is 0.9 repeating. Let me do that in a different color. I already said that s is 0.9 repeating. So these two things, since s equals s, 0.9 repeating must equal 1. And you might look at this and say, okay, well, that's pretty gimmicky. If you're not totally convinced by this, let me show you another way to do it. And I think I think someone in 8th grade could follow this, someone with 9th grade or 10th grade. So if you're in this range, you can probably follow the proof I'm about to show. And if you have a math background higher than this, then you definitely should be able to follow this. So let me just clear this. Let's talk about geometric series. What is a geometric series? Well, basically, if you have, say I had s and I said it was equal to 1 plus r squared plus r cubed plus up to r to the capital N. My question is there a more convenient way to write this down? Well, there is, and this is a geometric series right here. Let me show you why. If I multiply s by r, then I'll multiply each of these terms by r when I distribute. So the 1 will turn into an r, the r will turn into an r squared will turn into an r cubed, and so on until we reach, there's a term before this, there's an r to the n minus 1 term here. That would become r to the n. And then this term right here is going to become r to the n plus 1. The trick is, if you subtract these two quantities, so if I were to subtract s from rs, well, nothing's going to happen to the 1, but as you can probably see, we just changed the color, this r and this r is going to cancel, this r and this r is going to cancel, so on. R to the n is going to cancel with r to the n is going to cancel with r to the n. There's an r to the n minus 1 here that's going to cancel with this guy. And what you're left over is these two terms. You're going to be left over with a r to the n plus 1 and a negative 1 since I'm subtracting. So in summary, what you're going to get is you're going to get rs minus s is equal to r to the capital N plus 1 minus 1. And we can actually simplify s because I can factor an s out here. So I get s times r minus 1 equals to the r to the n plus 1 minus 1. And then I can divide both sides by r minus 1, and then I get s equals r to the n plus 1 minus 1 over r minus 1. And it's actually more commonly, this is actually more commonly written as s equals 1 minus r to the n plus 1 over 1 minus r. This is usually how it's written. The reason for that is because usually r is less than 1, at least in absolute value. So usually you're going to get like an r like 0.5 or something like that. In which case, if you were to plug it in here, you're going to get a negative value. But if you had r equals 0.5 here, you're going to get a positive value. So it's just usually with geometric series, you're dealing with numbers that are, usually you're dealing with an r where the absolute value of r is less than 1, usually. Okay. Well, how is this useful? Well, basically what I just showed can be used to simplify the term 0.9 repeating. Because 0.9 repeating is 0.9999, so on. Well, what is that? Well, that's 0.9 plus 0.09 plus 0.009 plus 0.0009, and so on to infinity. Well, what is this? Well, this is 9 times, well, actually, I'll do it a simpler way. This is 0.9 times 1. This is 0.9 times 1/10. This is 0.9 times 1 over 100. This is 0.09, oh, not 09, 9 times 1 over 1,000. And you're going to start to see the geometric series show its face. One sec while I scroll down a little bit. Because I can factor out the 0.9, and when I'm left with them, let's say 0.9 times, now here's what I'm going to do. I'm going to say that 1 is 1/10 to the 0. Well, I might not even do that. I'll leave it as 1. 1 plus 1/10 plus 1/10 squared plus 1/10 cubed ad infinitum. And now you see the geometric series here. And what I just showed was that if you have a series like this, in this case, r is equal to 1/10, I just showed that this whole series is equal to 1 minus r to the n plus 1 over 1 minus r. Well, what is n? Well, n is kind of infinity because this is non-ending. This does not end. This is going to go on to infinity. The highest exponent is infinite. It's just going to keep going. So that might seem like kind of a problem until you realize that 1/10 to the n is getting larger. Getting smaller. This is approaching 0. As n approaches infinity, this is getting smaller and smaller. You can see a tenth, 100, 1,000, a millionth. It's getting smaller and smaller. So as n gets large, this is going to go to 0. So you're just going to have a 1 in the numerator. Okay, well that takes care of the n, and now I'm just left with this whole thing is equal to, don't forget the 0.9, maybe I'll relabel that as 9/10, times 1 over 1 minus r, which is 1/10. Okay, great. So this is going to be 1 over 9/10 times 9/10, and that is 9/10 times 10/9, and that's 1. There you go. No surprise there. Well, there shouldn't be any surprise there that this whole series comes to be 1. So this is perhaps a more convincing way to show, because I just rewrote the way I just rewrote 0.9 repeating. And it turns out that the geometric series told me that this should be 1. And maybe you're not convinced. Maybe this part's holding you up. But I'll tell you this. You go and watch any video on limits, which is what I will eventually do a video on. This is going to start to become a lot more convincing. Anyways, I'm out of time. See you later.